Good afternoon, everybody. I'm Joshua Seymour. I'm an ocean engineering student here at the University of Southern Mississippi. This is my senior project for both my honors thesis as well as for projects and design for our program. This is on cellular telemetry for real-time river flow velocity data from Fluvial Acoustic Tomography loggers. You'll hear me refer to this as FAT. So some of the motivation behind my project is I've worked in close collaboration with Dr. Modular on a few different research projects, mainly on the fluid acoustic tomography system that he's had deployed in the West Fork River since 2021. This is an aerial view of the deployment. This is kind of showing a little zoomed out view to kind of see where we're at in Louisiana. FAT systems measure river flow velocity using travel time differences of sound pulses between two different logger units placed on opposite river banks. The way this works is you would deploy transducer and logger on one side, one on the other, and it's not perpendicular to the direction of the flow of the current. And essentially what happens is the sound that is going across the river that is slightly against the current is going to arrive at the opposite shore slightly after the one that's going with the current. These systems have high resolution, it's 115 hertz, section averaged flow velocity data. It doesn't require anything to be in the middle of the stream of the river, so there's no boat impacts or kind of impedance on the actual flow that's there. Currently, data from these systems has to be manually retrieved, so the researcher has to go to the test site. They either have to pull the SD card that contains the data, or they have to secure the shell into the system and download the data that way. It's simple to do, but it's time consuming. This is time that can be better spent on further developing the system itself. So cellular telemetry automates this data transfer process, reducing field visits drastically and just freeing up more time for other parts of the research. So for a telemetry system to work, there's a few objectives that have to be met. One, it has to operate fully autonomously, so no user intervention. If something were to go wrong, it needs to be able to fix itself essentially. Also, data uploaded from the logger must occur at regular intervals. Now we can get as close to real time as possible. This is mostly because you'd be able to see data coming in, every minute or every hour, so to speak, and you can see when something actually goes wrong. So if you go a couple hours and you haven't received any data, there might be something wrong with the deployment, and then you can go out there and fix anything that can have gone wrong. Additionally, it needed to be designed for installation in the field without requiring the loggers to be removed from the field and potentially missing out on days or weeks of data. This next objective is something that I probably should have addressed sooner in the project, but it needs to be able to run on Buster OS. Buster OS is a Linux-based operating system that is a couple generations old, and this is what is running on the loggers themselves. So whatever telemetry system was developed, it would need to be able to communicate with this or just flat out run on Buster OS. Lastly, it has a minimum upload speed of 0.01 megabits per second. That's because each data file is approximately 20 kilobytes and one file is created every 15 seconds. So even though this is a really low upload speed, the system would have to, by minimum, meet this to keep up with the demands of that deployment. I considered several different communication methods. I looked at using Bluetooth Low Energy or Wi-Fi, but these were simply just too short range for remote installations. And it could have been possible if there was additional infrastructure, like if you had an area that you could install, say a Wi-Fi router that everything talk to. But this would require additional installation into the field versus something that could just run at the deployment itself. Also looked into LoRa, which is short for long range radio. This has pretty good ranges. This is free to use. It's part of the ISM bands, which is industrial, scientific, and medical bands. This runs on the 915 megahertz radio waves. Unfortunately, though, it wasn't really viable for frequent 20 kilobit files every 15 seconds. The FCC has regulations on how much time you're allowed to spend on these bands, how much data you're allowed to transfer, etc. Also, LoRa is kind of susceptible to what is called smart meters, which is how utility companies like water, power, gas, how they monitor your power usage and your gas usage. They also operate on the same band, so LoRa is really susceptible to interference from those. So in conclusion, I went with cellular. It offered the best balance of range, bandwidth, and reliability for the deployment. So before I get into the cellular itself, some of the tools that I use when writing the software for the data telemetry itself. are listed here. So the first one we see here is Samba. Samba is an open source software that allows communication between Linux and Windows devices, or between Linux and Linux devices. It uses the server message block, or Common Internet File System protocol. This is a good way to describe this is if you take a USB drive that has data on it or files on it, and you plug it into your laptop, you're able to see those files on the USB, but those files do not exist on your computer. It's just visible to your computer. So this will be talked about in a couple slides how I utilize this. rclone is a command line program used for managing files between local and cloud storage. And this tool was specifically used to upload data from a particular folder to a OneDrive account. Next is an access point. Best way to think of this is if you turn a mobile hotspot on your phone and you're able to see your phone on your available Wi-Fi networks, that's an access point. So part of the system actually operates as an access point. That way the data can make it from the logger to the telemetry system itself. And last here is cron. Cron is a Unix-based task scheduler. You can set certain things to execute, let's say every minute, every hour, or you can say I want this certain thing to happen at 12 o'clock every day. It's just a simple task scheduler where you can handle a lot of autonomous tasks with just 1 or 2 lines of code. The physical components of the system are pretty simple. On the left here we see a PiTalk 4G Internet of Things dongle. This is an open source cellular modem that uses a Quectel EG25G modem. This modem is able to connect to cellular networks pretty much globally, for sure in North America, Europe, and Asia. So I specifically chose this mostly because of the modem and the fact that this has 2 different ways to interface with the modem itself. So it's got a USB-C here, female port, and it has a USB-A port there. So it opened up a lot of opportunities for different ways you can interface with the modem itself. On the right, we see a Raspberry Pi Zero. So earlier I mentioned that the system has to work on Buster. So the actual firmware that I wrote will not run on Buster. So this Raspberry Pi Zero, it runs a much more modern operating system called Bookworm, and it acts as the intermediary device between the logger itself and the telemetry system, which is basically the software that I wrote. The Pi Zero is much newer than the Pi 2 that is on the loggers. So even though it's much smaller and lower power, it's actually quite a bit more powerful. It also has onboard wireless capabilities like Wi-Fi and Bluetooth. So this is a system diagram showing how everything works. On the far right here, we see a Raspberry Pi 2B, which I'll refer to as Logger Pi. This is the Raspberry Pi that is integrated within the loggers themselves. And this is where all the data is stored. Excuse me. So the data is actually stored on here on a folder called Tomo. So when I mention Tomo, that's what I'm talking about, it's just the data files. And the way this works is this is configured to connect to the access point that I have hosted on the Raspberry Pi Zero. And using Samba, the contents of the Tomo folder, which is all the data, like I said, is visible to the Pi Zero. The Pi Zero I'm going to refer to as TelePi. It runs the entire telemetry system, all the automation scripts that I wrote run here, and how it's currently configured. Once per minute, it uploads all the data through the modem view. So it's going through Cellular. It uploads all the data to OneDrive using that rclone command, or that rclone program I was telling you about. So it's a very simple system. It's just 2 additional components that has to be added to the current standing Fluvial Acoustic Tomography logger. This is the actual automation that's occurring on the system. So I have a little bit of color coding here. Everything in purple is happening at a system level. So this could be cron jobs or actual system services. System services are what's happening during boot. So when you boot up something and you see a bunch of lines of code running, that's just the boot process essentially. So one of those things that's occurring during that boot process is this one here called Start AP. This enables the access point to make sure it's visible to the logger itself. And then a cron job runs this PiTalk boot.sh script. This is a custom script that I wrote that essentially it initializes the cellular connectivity, and currently it's set to connect to T-Mobile's network using a Mint Mobile SIM card, but that can be changed to basically any cellular network carrier in North America, Europe, or Asia. Another automation of it, it's a cron job runs every 5 minutes, which executes the check and boot script. This is a watchdog script that ensures that cellular connectivity is online, and if it's not, it reruns the PiTalk boot script and reestablishes cellular connectivity. And also, it actually looks for a static IP address for the access point, and if it is not there, it means the access point is not online, so it reruns the start AP script to reestablish that access point. Lastly, this is the most simple part of our project, but probably the most important. Every minute, the script that's titled sync tomo, which is literally a one-line script, it uploads the contents of the data folder called tomo to OneDrive. And this is pre-configured to go to a specific folder on a specific OneDrive account. The way the data flows through the system is the logger saves data to that folder I was talking about earlier, tomo. The logger is connected to TelePi via the access point. Samba mounts tomo to the TelePi, meaning the TelePi is able to see the data that's there. TelePi is connected to the internet via cellular, and then, like I said previously, once per minute, sync tomo runs, and all the data is sent to OneDrive. To ensure that this worked, I did numerous bench tests as well as field testing. And what we're seeing here is actual data that exists on the logger. And essentially what this line of code is saying is, I want to see the last 10 files. So I ran this on the logger, and then I ran the same thing on the TelePi simultaneously. You can see that there's data points 274 through 282. These exist on both the TelePi and the logger, showing that the access point's working and Samba is working. Then simultaneously I logged into my OneDrive account and I found the same data files there showing that cellular networking is online and Arcom is working properly. Also did a similar test in the field and found that I was getting upload speeds around 500 times the minimum. Some of the skills learned during this is I learned a lot about system configuration and networking, cellular connectivity, scripting and automation, data sharing and cloud synchronization, system integration, and cross-platform interfacing. Even though I was mostly going from Linux to Linux, it was still nice being able to use rclone to take data that was stored on a Linux-based device and upload it to a Microsoft-based cloud service. The budget behind this project, I was awarded the D-Curd-Eaglesburg grant, so I was awarded $1,000 to complete this project. This paid for 2 Raspberry Pi Zeros. They're kind of inexpensive. You can get them anywhere from $15 or for some reason these are $23 wherever they were ordered. I had to get 2 PiTalk 4G Internet of Things dongles, and I had some miscellaneous prototyping, cable, SD cards, stuff like that, just to kind of aid in completing the project. And I was also awarded a $500 stipend for my time. A couple of things I would like to do with the system in the future. One on the left here is probably the most important to me is I'd like to upgrade the logger itself to use a Raspberry Pi 5 so we can run the 64-bit bookworm operating system. That way the telemetry system can run directly on the logger itself. It wouldn't really need the TelePi, so cut the cost a little bit. But also this is just a much faster processor on this computer. Additionally, I would like to integrate they call it a serial HAT. HAT just means hardware attached on top. But I'd like to integrate a serial HAT into this. That way you could actually connect the serial output of a charge controller directly to the logger itself. That way you wouldn't only be able to get your Fluvial Acoustic Tomography data, but you'd also get data on your battery health and solar and stuff like that to kind of keep an eye on the power requirements of the system. In conclusion, this system is fully successful. It's capable of providing real-time data feeds from FAT systems, and theoretically can do this globally. I want to thank Dr. Madi Razaz as my advisor for this project, as well as advising me on my honors thesis about the same project. And thanks to Dr. Garo Newts for his feedback on the documentation and presentations about this project. And lastly, for D-Curd for funding this project. Questions?
What would you say was the most difficult thing to overcome within the scope of your project?
Finding out last minute that the operating system on the loggers was substantially older than assumed. It had been something for me to check. It never dawned on me to check on it until much later. But as an aside to this project, I am developing a cluster version of the system, but bodies advised me to not even worry about it, but just upgrade the Raspberry Pis that are in there.
Is your system currently activated onto the FAT systems, or?
No, so I actually only have one of the Raspberry Pi Zeros right now, so I would only be able to get data from one side of the system.
Okay.
They're probably actually in the mailroom right now, so I got them. But before I do that, I need to install a buck converter to power the system separately. It would use the same power that the logger is currently using, so it's the same battery, whole 9 yards. But we wanted to boot up sooner than the Raspberry Pi that's there. So if it was just plugged into that Raspberry Pi, the Pi 2 would have to boot first, and then the Telepi would boot. We want this to boot before that, so I'm going to go direct to it's actually going to be on the toggle switch.
Okay.
That way, as soon as you turn the switch on, Telepi boots up, then it handles all the GPS aspect of the FAT system, and then the FAT's logger boots up, which would be a little more streamlined that way. Okay.
I know earlier in the project you mentioned exploring mismatched data and fixing it. Is that something that's still implemented in this current, or is that?
So that would happen basically on shore, so to speak. So that won't happen on the logger itself. It will happen during post-processing. So once data's been retrieved, you could actually line up 2 windows of data files and you can compare them that way manually. But something on shore, so to speak, is going to handle that aspect.
How hard would it be to implement it into the actual logger themselves?
So it would be difficult to implement the actual logger itself, but the fix to having mismatched data is actually deleting a data point, and doing that on the logger could potentially have toward accidental deletions. So it'd be better to have that done just for the desktop computer, and you just have a simple script that's just reading file names and comparing them, because it really just looks at, let me go back a few slides. So it actually looks at this number. When the file name starts with a 1, that's actually FAT system 2. It starts with 0, that's FAT system 1. And it's basically lining up these file names, which is actually just a date code, date and time code. So what it would do, you gotta go through there, look at the file names and say, okay, I have a 0 file that ends in 282, but I don't have a 1 file that ends in 282. So then it would just either quarantine or delete that extra file, so to speak. And you would miss out on if it's just 1 file, you'd be missing out on just 15 seconds of data. If I had something running on the system and something went wrong, it could be deleting days. So don't want that.
What would cause a file to not be generated?
If for whatever reason the opposite shore didn't it could receive the signal, but it could potentially not record the receiving time. Lottie said it's happened very rarely, but when it does happen, it skews all your data. And since it's just a matter of going through the file names and seeing when there's a mismatch, a lot of times you can actually say like, there's 5,760 files in this folder, there's 5,760 files in this folder. You know you're good. So it's an easy fix when it actually happens. It happens very infrequently, but if it does happen, it kind of ruins all your data. But all you have to do is just go through, delete that extra file, and then just rerun your processing.
More questions from you? You mentioned that the LoRa uses the ISM band. Do you know what band the Wi-Fi and the Bluetooth are using?
No, it's off my head.
Same band.
It is? Okay. So they could potentially be interference as well.
Mm-hmm.
So, okay.
Yeah, everything you don't pay for is ISM.
Really?
Pretty much. That's kind of what distinguishes it. Those are the free bands, the ISM bands.
Gotcha.
Everything else, cellular, you pay for because they use
Right.
bands they actually have to pay for.
Right.
All right, let's give him another hand.